IB Physics, Standard Level, Paper 1, November 2022. Problem number 1. A rectangular sheet of paper has dimensions of 30 plus or minus 0.5 centimeters and 20 plus or minus 0.5 centimeters. What is the percentage uncertainty of the perimeter of the paper? Perimeter is 2 times length plus width, so it's 100 centimeters in our case. The percentage uncertainty, this is the ratio of absolute uncertainty to the value of the perimeter itself. The absolute uncertainty of the perimeter is 2 times delta length plus delta width. Delta length and delta width are 0.5 both. So we will get 2 centimeters for absolute uncertainty of the perimeter. So actually I can say perimeter equals 100 plus or minus 2 centimeters. So the percentage uncertainty, this is 2 divided by 100, so it's 2%. The problem number 2, two forces F and G act on a system. F is reversed in direction and G is halved. Which vector correctly represents the new resultant force? So, okay, we reverse the force F. So now it's like this. And we halve the force G. So now we get these two blue vectors, and the resultant force, the net force, is the red vector. So we can see it has 1 square vertically and 4 squares horizontally. Which option is okay for us in this case? This is the option D only, the closest option, but I think they did a mistake here, because actually this vector has to have 4 squares horizontally here, but they have only 3. But okay, this is the closest option here, option D, of course. Number 3. Ball 1 is dropped from rest from an initial height h. At the same instant, ball 2 is launched vertically upwards at an initial velocity u. At what time are both balls at the same distance above the ground? So we will say that when they at the same distance above the ground, they have the same position, y1 equals y2. For the final position of the first one, we can say that it's h, which is initial position of it, minus gt squared over 2, minus because g is opposite to the y-axis. And for the second ball, y2, the final position of the second ball equals 0, the initial position of it, plus ut minus gt squared over 2. Again, it has the same acceleration directed downwards against to the y-axis, so it's negative as well. And then we just equal them, and we will get this equation, and we will get that t equals h over u. So this is the option C. A projectile is launched with velocity u at an angle theta to the horizontal. It reaches a maximum height s. What is the time taken to reach the maximum height? Is a projectile motion problem. We know that at this point, with maximum height, the velocity, the vertical velocity is 0, and we have only horizontal velocity, horizontal component. So if the vertical velocity is 0 here, we can say that the initial vertical velocity, v initial y, equals gt, right? I hope you understand this equation. If it equals gt, so we can say that t equals v initial y over g. But v initial y also equals u sine of theta, because you can see from this triangle that this is the opposite to the angle theta here, and u, this is the hypotenuse. So yeah, u sine of theta, this is the v initial vertical, v initial y. So we get the option D, u sine of theta over g. Number 5. An object of mass 2 kilograms is on a horizontal surface. The object is pulled by a force of 12 newtons and accelerates at 2 meters per second squared. What is the coefficient of dynamic friction between the object and the surface? Easy dynamic problem. So let's show the forces here. The force that we pull with, the normal force, the weight, friction, and then just use the second Newton's law for both directions, horizontal and vertical one. So weight equals N equals mg, F minus friction equals ma, and friction also equals mu N, which is mu mg. So friction equals F minus ma, mu mg equals F minus ma, and mu, the coefficient of friction, equals F minus ma over mg, which is 0.4. This is option B. Number 6. A person lifts a total mass of 20 kilograms through a vertical distance of 0.6 meters. The person repeats the lift n times to transfer total energy of 6 times 10 to the power 4 joules. What is n? The total energy that he transfers equals the total work that he does. And work equals force times distance, but force in our case equals mg, right? The weight of the load. And he does it n times. So we derive n from here. It equals E total over mgs. Just substitute the numbers and we will get 500 times, option C. Number 7. A ball of mass 1.5 kilograms strikes a force sensor and bounces. The ball experiences a change in velocity of 10 meters per second. The graph shows the variation with time t of the force F recorded by the sensor. What is delta t? So we know that the change in impulse, no, we don't say like this, we say change in momentum equals the net average force times time that it acts on the object. So delta p equals F average times delta t, and delta p also equals m delta v, right? So m delta v divided by F average equals delta t. What is F average? We can see that the relationship of the force and time here is linear. So it means that we can find the average value, like just initial one plus final one over 2, right? Initial force, which is 0, plus final force, which is 100, divided by 2. This is 50 newtons. And here it's the same, 50 newtons as well. So the total average force here for this delta t time is 50 newtons. 50 plus 50 over 2 is 50 as well, right? So we divide by 50 and we will get 0.3 seconds, which is option B here. Number 8. A block of glass of mass 5 kilograms and temperature 30 degrees Celsius is brought into contact with a block of asphalt of mass 20 kilograms and temperature 75 centigrades. The specific heat capacity of asphalt is twice that of glass. No energy is transferred to the surroundings. What is the final temperature of both blocks? Typical thermal equilibrium problem. Here we will say that the heat that asphalt gives to the glass, which is this one, equals to the heat that glass gets from the asphalt, which is this. So Ma, this is the mass of asphalt. Ca, this is the specific heat capacity of asphalt. Delta Ta, this is the change in temperature for asphalt block. The same for glass here. Delta T asphalt equals T initial of asphalt minus T final by magnitude, yeah. And for glass, this is the final minus T initial of the glass. Then we just solve the equation, rearrange it, derive T final, and we will get 70 centigrades, which is option D. Number 9. A solid mass gains energy at a constant rate until it reaches its liquid phase. The specific heat capacity in the solid phase is greater than in the liquid phase, which graph shows how the temperature of the mass varies with time. C and D not our options for sure, because we don't have this region of melting. We have the melting regions only in options A and B. And our option is B, because they say that in solid phase the specific heat capacity is greater than in the liquid phase. If specific heat capacity is greater, it means it's harder to change the temperature of this body. So it means that the graph has to be not so steep, less steep. It has to be less steep. And we can see it in option B. Here it's less steep than here. And you cannot say the same about this, right? So it's option B for sure. Number 10. 3 statements about Boltzmann's constant are: Boltzmann's constant has a unit of joules per Kelvin. Correct. Boltzmann's constant equals gas constant divided by Avogadro's constant. Correct. And Kb equals the average kinetic energy of particles over temperature of the gas. Almost correct. It's proportional to it but not equal, because we have some coefficient here, so it's not correct. The right option here is A. Number 11. An object oscillates at the free end of a vertical spring. The graph shows the variation of the object's position with time. At which position does the object have zero velocity and a negative acceleration? This is the position A, because at the position A, the load is here, and the force of the spring acts on it like this. F spring. So the acceleration is directed downwards. The net force is directed downwards, the acceleration is directed downwards. So the position axis is upwards, so the acceleration is negative. And of course here we have zero velocity, because this is the maximum amplitude, maximum displacement from equilibrium position point, right? So the velocity is zero there. Number 12. The graph shows the variation with distance x of the displacement of the particles in a wave. The frequency of the wave is 600 Hz. What is the speed of the wave? This is the snapshot graph here, a snapshot graph, and we can see that the wavelength lambda equals 4 millimeters here. 4 millimeters, or 4 times 10 to the power of minus 3 meters, right? And we know that the wavelength equals the velocity of the wave times period of the oscillations of this wave, or the velocity of the wave, the speed of the wave, divided by frequency. We just substitute it. So the speed of the wave equals the wavelength times frequency, which is 2.4 meters per second in this case. Option D. Number 13. A point source emits a sound wave of amplitude Z. A person stands a distance L from the source. The amplitude is changed to double Z. What distance must the person move through in order to hear the original intensity again? We know that intensity is directly proportional to amplitude squared. So if we double the amplitude, it will affect intensity which way? Intensity will be greater by a factor of 4, right? Because it's amplitude squared. But also we know that intensity is inversely proportional to distance squared. So it means that if we want the intensity to be the same, we have to increase the distance by the same factor, by a factor of 2. Because if we increase distance by a factor of 2, intensity will be decreased by a factor of 4. So simultaneously it's increased because of the amplitude by a factor of 4 and decreased by a factor of 4 because of the distance increasing by a factor of 2, right? So the person has to stand away, move away, one more L, right? So the person will have double L distance from the source, so distance will be doubled and intensity will be the same again. Option A. Number 14. A ray of light enters from air into a water droplet of radius r at point S, as is a vertical distance h from the center of the droplet. The droplet has a refractive index n and the angle of refraction is theta. Okay, we will just use Snell's law here. We know that sine of theta 1 divided by sine of theta 2 equals n2 over n1. Sine of theta 1 over sine of theta 2 equals n2 over n1. And 2 and 1, what the index is? The index is for mediums. Second means second medium, the medium where it refracts, and the first medium, the medium where it goes from. So the first medium in our case, this is the air, and the second one, this is the water. The index of refraction of the air equals 1. So this n1 is just 1. N2, let's denote it as just n, and theta 2, let's denote it as theta because it's actually theta here. So sine of theta 1 divided by sine of theta equals n. Sine of theta from here equals sine of theta 1 over n, and we can see from this triangle that this angle is the same as this angle, theta 1. So h is opposite to this angle, so h over r, this is the sine of theta 1. So sine of theta equals sine of theta 1 over n, which is h over r over n. Option C. Number 15. A standing wave is formed in a pipe closed at one end. The third harmonic has a frequency of 400 Hz when the speed of sound is 300 meters per second. What is the length of the pipe? If it's a pipe closed at one end, the first harmonic is like this. So the wavelength of this standing wave equals 4L, where L is the length of the pipe. Or length equals the wavelength over 4, right? But for the third harmonic, by the way, notice that it doesn't have even harmonics, only odd harmonics. First one, third one, fifth one, and etc. So for the third one, the wavelength equals 4L over 3. Or length equals 3 lambda over 4. You can see it here in this animation. You can see that, yeah, it's true. It's really like this. So we will use this to solve the problem, of course. We will say that F, we know F equals 400 Hertz. V, speed, equals 3 meters per second, 300 meters per second. We also know what? That this is the third harmonic in a closed pipe that is closed at one end only. So we know that the length equals 3 over 4 lambda, right? Also we know that lambda, the wavelength, equals v, the speed of the wave, divided by frequency of this wave. So we will get that L equals 3 over 4 lambda, but lambda is v over f, so it's 3 over 4 v over f, which is 9 over 16 meters. Option B. Wire X and wire Y are connected in series in a circuit. Wire X has 3 times the radius and 1/3 the charge carrier density of wire Y. What is the ratio of drift speed in X to drift speed in Y? To solve this problem, we have to know that current in a wire equals the charge carrier density M times charge times cross-sectional area times drift speed. From this equation, we can see that the drift speed is inversely proportional to the charge carrier density and cross-sectional area. We know that the cross-sectional area is the area of a circle, right? So it's pi r squared, which means that the cross-sectional area for which one? For X is greater by a factor of 9, yeah? 3 squared, a factor of 9. So AX equals 9AY. And then we will use this. We will say that Vx over Vy, this ratio, equals Ny over Nx times Ay over Ax, which is Ay over Ax equals 1 over 9, right? And Ny over Nx equals what? Ny over Nx equals 3, right? So it's just 1/3. Option B. Again, they told us that 1/3 of Ny equals Nx. That's why I solved this like this. That's why I used it here. Number 17. A cell of negligible internal resistance is connected to 3 identical resistors. The current in the cell is 3 amperes. The resistors are now arranged in series. What is the new current in the cell? So easy problem, super easy. First we have R, so the total resistance, R total, equals, here we have a half of R, right? So it's 1.5 R. And when we will rearrange it, it will have 3R resistance, right? So 3R, R total prime equals 3R. So it means that the resistance is increased by a factor of 2. So if we have the same voltage here, the current has to be decreased by a factor of 2. So if the initial current is 3 amperes, the final current has to be equal 1.5 amperes, which is option B. Number 18. What is correct about the energy changes and the terminal potential difference during the discharge of a practical electrical cell? Energy changes, terminal potential difference. Here, of course, we will have option chemical energy is transferred to electrical energy. It's correct. Decreases significantly at the end of the cell lifetime. Of course, this is option B. Only option B is correct here. Number 19. A loop of wire lies in a magnetic field directed into the plane of the page. The loop carries a current in a clockwise direction. The magnetic force acting on the wire tends to... Okay, here we just have to apply Fleming's left-hand rule. And if we apply it, we will see that the force of magnetic field tries to increase the radius of the loop. Option D, right? Because it acts on it like this. Do you know why? Can you use this Fleming's left hand rule to determine the direction of the force? Number 20. A car on a road follows a horizontal circular path at a constant speed. What is the direction of the net force acting on the car and the direction of the instantaneous velocity of the car? Pretty easy problem again. So direction of the net force for sure has to be directed towards center of the circle. So it's either C or D. And the direction of instantaneous velocity is always tangent to the circle, so it's option C. Number 21. A mass attached to a string rotates in a gravitational field with a constant period in a vertical plane. How do the speed of the mass and the tension of the string compare at P and Q? At point Q, we have the gravitational force. The weight is like this, right? Here the weight is like this as well. But tension is directed upwards here, and it's directed downwards here. Yeah. So we can say that TQ equals M G plus A, or A plus G, no difference, and TP equals M A minus G. So for sure T at point P less than tension at point Q, right? So our option is B or D. And also they say that the period is the same, and I would say that this is the option B, that speed of the mass is the same and the tension is greater at point Q. But if we think about this problem, like if we use our imagination and we don't think about it in a way like they use something special to make the speed of this object like the same at each point. Actually, if I just do like this, like they do in this problem, I can see that the velocity at point P, the speed at point P is for sure will be less than at point Q. And I will choose the option D, which is correct option. I already checked. But I think that here students can also choose the option B as well, because it's not so clear here which option we can choose, B or D. But the correct option is D. Number 22. The center of the Earth and the Moon are distance d apart. There is a point X between them where their gravitational fields cancel out. The distance from the center of the Earth to X is d, small d. The mass of the Earth is capital ME and the mass of the Moon is capital MM. What is correct at X? Okay, here you have to do some calculations. You know that forces has to be the same here, here and here. Force from the Earth and force from the Moon, right? They have to be the same. So G M Earth over what? Over D small squared has to be equal G M Moon over, what is this? D capital minus small d squared, right? Right. We'll lose our G, we'll lose M, and we will get option C, right? Yes. 23. A nucleus of krypton decays to a nucleus of bromine according to the equation. What are Y and Z? Atomic number is the same. One of these particles carries 1 unit of charge. So no mass, 1 unit of charge. What is this? This is positron for sure. Y is positron. It's 0, 1. And if we have positron, we also have neutrino here. This is neutrino. And our option is option A, positron and neutrino. If it would be electron, it would be antineutrino. But this is positron in our case, we can see it, so it's neutrino. You have to know about this to solve this problem. 24. Which development in physics constituted a paradigm shift? The classification of variables into scalars and vectors, for sure not. The determination of the velocity of light in different media, no. The equivalence of F equals ma to F equals delta P over, no. The equivalence of mass and energy, for sure, yes. Because paradigm shift is a new conceptual framework. Relativity of quantum mechanics. So option D. Number 25. A fusion reaction of 1 nucleus of hydrogen 2 and 1 nucleus of hydrogen 3 converts 0.019 U to energy. What is U? U, this is the atomic unit of mass, right? A fission reaction of 1 nucleus of uranium 235 converts a mass of 0.19 U to energy. The specific energy, this is the energy that is released per unit mass of fuel. And energy released is proportional to the mass converted, because according to the famous equation of Einstein, E equals delta mc squared, or delta E equals delta mc squared. The change in mass just converts into energy. And we want to know the ratio of specific energies of these two reactions. For fusion reaction, we have H2, hydrogen 2, and we have plus H3, hydrogen 3. So the total mass is 5U. What is U? U, this is the atomic unit of mass, which equals approximately, as I remember, 1.66 times 10 to the minus 27 kilograms, if I remember correctly. But we don't really need to remember this here. We just will say that the specific energy of fusion reaction, specific energy fusion, is proportional to 0.019 divided by 5, because we just lost our units of atomic mass here. And about fission, let's say fission uranium 235. For these, the mass converted is 0.19 U from given, and we know that here the specific energy of fission is proportional to 0.19 over 235. Again, we just lost these units. So then the ratio fusion over fission is 0.019 over 5 over 0.19 over 235, which is Approximately, it's about 4.7, which is approximately 5. So it's about 5 times greater, right? So fusion releases much more energy, 5 times more energy per kilogram than fission. And our option is C. Number 26. 3 statements about the atom are: the nucleus of the atom is positively charged. Correct. The electrons provide only a small fraction of the mass of an atom. Correct. Most of the atom is free space. Correct. So the option D. 1, 2, and 3, they are all correct. Number 27. The electromagnetic spectrum radiated by a black body at temperature T shows a peak at wavelength lambda peak. What is the variation of lambda p with T? To choose the correct graph, you need to know the most important equation here. And this equation is about Wien's law. Wien's law says that lambda peak equals W, which is Wien's constant, it's just a constant, over T, temperature of this body. So the wavelengths, the peak wavelengths, is inversely proportional to the temperature of this body. And only graph A satisfies, right? Only graph A is okay, because this one is linear, no, and this one is, of course, no. Only option A shows us the proportionality like this between them. Number 28. Water is to be pumped through a vertical height difference of 12.5 meters. The pump is driven by a wind turbine that has an efficiency of 50% and an area swept by the blades of 100 meters squared. The average wind speed is 5 meters per second, and the air density is 1.2 kilograms per meter cubed. What is the maximum mass of water that can be pumped every second? This problem is interesting. Let's solve it. So we have the density of air. We know the speed of the wind. We know the efficiency. We know the area. And we know delta H. We want to find what is the maximum mass of water that can be pumped every second. Okay, we want to find m, mass of water, over T, over time, right? How we will do this? For sure, we will change the potential energy of this water. We will change it by mg delta H, right? If we lift it. And how we do this? Actually, the wind does work here. The wind applies pressure, right, to the blades, and this pressure, we can say that the pressure of air equals the density of the air times the speed of the air squared over 2. This is the pressure that air applies to the blades. And we know that pressure times area equals force, and force times displacement equals work. Very nice, very nice. So let's say it's density times v squared over 2 times A times S. Also, not all the work goes there, right? Only half of this work, 50% efficiency. So 1/2. And what else? That's all. Now let's divide let's divide this equation by time. By time. We divide it. And we will get velocity, we will get the speed again. S over t, this is the speed. So we will get, what we will get? We will get mg delta h over t equals density times velocity cubed, right? Times area divided by 4. Is it correct? I think yes. So from here, m over t equals density times area times speed cubed over 4gh, delta h. And this is, let's calculate it, 1.2 times 100 times 125 over 40 times 12.5, and we will get 30 kilograms per second. Option B. Number 29. When heating a metal rod at one end, thermal energy is transferred along the rod. Which statement explains this transfer? Free electrons transfer kinetic energy to the ions in the metal. Actually, yes. It's option A. Number 30. Planet X and Planet Y both emit radiation as black bodies. Planet Y has twice the surface temperature and 1/3 of the radius of Planet X. What is the ratio of power radiated by Planet X to power radiated by Planet Y? Oh, to solve this problem we need to know the Stefan-Boltzmann law. Stefan-Boltzmann law says that the power radiated by black body equals sigma times area times temperature to the power of 4. This is the Stefan-Boltzmann law. So we can say that this power is proportional to area and temperature to the power of 4, because this is just a constant. Sigma, this is the Stefan-Boltzmann's constant, which equals, by the way, 5.67 times 10 to the power of minus 8 watt per meter squared per Kelvin to the power of 4. But you don't need to know this information really here now. You just have to know that we have planets, so the area equals 4 pi r squared. 4 pi r squared. So area is proportional to r squared. And if the power is proportional to area, power also proportional to r squared and proportional to the temperature to the power of 4. Then I can say that the ratio in this case, px over py, equals rx squared over ry squared times tx to the power of 4 over ty to the power of 4. And we will get 9 over 16 here, which is option A. IB Physics Standard Level, Paper 2, November 2022. The problem number 1. A raindrop falls vertically from rest. State the initial acceleration of the raindrop. Of course, it's just g. A equals g, approximately 9.81 meters per second squared. The graph shows how the speed of the raindrop varies with time t. Explain by reference to the vertical forces how the raindrop reaches a constant speed. So we know that force of gravity acts on it, mg, or you can call it just weight, right? And the drag force. The drag force is proportional, directly proportional to speed squared. And when we have enough speed, this force is equal to mg. So with enough speed, F drag equals weight, or equals mg. And when these forces are equal to each other, we have constant speed here, and it doesn't change anymore, as we can see on the graph. By the way, we call it terminal velocity. This velocity, we call it terminal velocity. During the first 3 seconds of motion, the raindrop falls a distance of 21 meters and reaches a speed of 9 meters per second. The mass of the raindrop is 34 milligrams. The temperature of the raindrop doesn't change. Determine the energy transferred to the air during the first 3 seconds of motion. State your answer to an appropriate number of significant figures. Okay, let's do it. So we know that time equals 3 seconds. We know S equals 21 meters. We know V, final V, equals 9 meters per second. We know mass, the mass is 34 milligrams, and T is constant. The temperature is constant. So how can we find this energy transferred to the air? Actually, if there is no drag force, the kinetic energy of the drop will be E kinetic no drag equals mv no drag squared. So the velocity that it will reach if there is no drag, over 2, right? And how to find this velocity? V no drag. Oh, it's very easy. It's just gt, right? So ek no drag will equal to mg squared t squared over 2. But actually we have drag. We have the drag force here. So E kinetic, when we have drag, equals mv squared over 2, where v, this is that 9 meters per second, the real velocity that we have because we had drag force. By the way, you can see that if there is no drag, it will equal to 3 times g, it will equal 30 meters per second. But actually we have only 9 meters per second, right? And you can calculate this, and you can calculate the change. So ek no drag minus ek with drag equals delta E, and you can calculate this. It will equal 0.5 m times g squared t squared minus v squared, about 5.6 times 10 to the power of minus 3 joules. Describe the energy change that takes place for t more than 3 seconds. We have no change in kinetic energy anymore after this, right? So we have terminal velocity there. The kinetic energy doesn't change, but potential energy is decreasing all the time. So where the energy goes? It goes to heat up the air, of course, again. Just all the energy change goes to heat up the air. That's all. The next problem, number 2. A solar heating panel is placed on the roof of a house in order to heat water in a storage tank. The rest of the roof is covered with tiles. On a certain day, the intensity of the solar radiation that is incident perpendicular to the surface of the panel is 680 watts per meter squared. The following data are available. Mass of the water in the tank, initial temperature of the water in the tank, specific heat capacity of water, overall efficiency of the heating system, albedo of the roof tiles, emissivity of the roof tiles. Determine the minimum area of the solar heating panel required to increase the temperature of all the water in the tank to 30 degrees Celsius during the time of 1 hour. Okay. Let's do this. So we know that we need to heat the water up, and the energy, this heat, we can write down the equation for this. Cm delta T, this is that energy that is required to heat the water up by 15 centigrades, right? It was 15, has to be 30, so 15 centigrades delta T. But also we know that not all of the energy goes for this. Only how much? The overall efficiency of the heating system, 0.3, 30% only. 30% only goes for it. So I can say that it equals this efficiency times E total. Let's denote it as E total. And E total in this case equals this energy E over efficiency, but this E, this is the heat, it's Cm delta T over efficiency, and they ask us for minimum area. How can we find this minimum area? We know that intensity times area equals power. Alright? We know that if we multiply it by time, we will get intensity area. Time equals power. Time, power, time, this is the energy exactly. This is our total energy, right? So area from here equals E total divided by intensity times time. Yeah, and we can substitute it. We can substitute E total from here, and what we will get? We will get Cm delta T over efficiency, intensity, and time, which is 1 hour. If we calculate, we will get about 21.4 meters squared. Estimate in centigrades the temperature of the roof tiles. The temperature of the roof tiles. Okay. How to estimate this temperature? For this, we will need Stefan Boltzmann's law again. The power that is radiated by a black body equals sigma area T to the power 4, and intensity that is emitted, right? Let's denote it as I0 emit equals the power over A, over area, and it equals sigma times T to the power 4. So we just lose the area if we divide it by area. And the real intensity that is emitted is epsilon sigma T to the power 4, where epsilon, this is the emissivity, because our body is not the perfect black body, because this is for a perfect black body, but this one is not perfect black body. So only how much? The emissivity is 0.97, so 97%, only 97% is radiated, and we will use it here. Okay, how about absorbed intensity? I absorbed. Absorbed is 0.8 times 680, because only 80% is absorbed. They said albedo of the roof tiles equals 0.20, 0.2. So albedo, this is like how much it reflects. So it reflects 20% and it absorbs 80%. So 80% of this intensity is absorbed, which is by the way how much? 544 watts per meter squared. Absorbed. Okay, how about emitted intensity? Let's calculate this as well. We will get what? We will get here. We will get 0.97 times 5. Sorry, times 5.67 times 10 to the power of minus 8 times temperature to the power of 4. Yeah, we cannot find this emitted intensity because we don't know this temperature. Actually, we want to know this temperature. But what the trick here? The trick is that if we have some constant temperature there, it means that the emitted intensity and absorbed intensity, they're the same. They has to be the same. We have to have the thermal equilibrium. So in this case, I emitted equals I absorbed and then we say that this 544 equals this 0.97 times the Stefan Boltzmann constant, 5.67 times 10 to the minus 8 times this temperature to the power of 4, and we will derive this temperature from here. And if you derive it and calculate, you will get something about 315 kelvins, which is approximately 42 centigrades. This is the answer. There is an airspace above the water in the storage tank with an opening to the atmosphere. Assume that air behaves like an ideal gas. State one way in which a real gas differs from an ideal gas. We know that in real gases, molecules interact with each other and collide against each other in a not absolutely elastic way, right? So we can say that real gases have potential energy, intermolecular potential energy, but the ideal gas doesn't have. Also, we can say that the real gases could be liquefied, but the ideal one cannot be liquefied. We also can say something else, something more about this, but it's enough. Already it's enough to say here. I will not write it down. Enough to say. The airspace is always at constant atmospheric pressure and constant volume as the water level is kept constant. The airspace temperature and water temperature are the same. The water is heated. Explain why the quantity of air in the storage tank decreases. PV equals nRT. P is constant. P is constant in this case because it's opened right? So the pressure is atmospheric pressure. Also, the volume is constant as well. And we can see that if P and V is constant, then if the temperature is increased, right, the quantity of air has to be decreased here. And that's all. Explain why the quantity of air in the storage tank decreases, because temperature temperature increases, and PV is constant, R this is a constant, so of course N decreases. Another method of harnessing solar energy involves the use of photovoltaic cells. Distinguish between photovoltaic cells and solar heating panels. Photovoltaic cells produces electrical energy to heat the water, whereas heating solar panels just directly heat the water. And that's all. It's enough. Number 3. A string of length 0.8 meters is fixed at both ends. The diagram shows a standing wave formed on the string. P and Q are two particles on the string. The variation with time t of the displacement of particle P is shown. Okay. Draw on the axis a graph to show the variation with t of the displacement of particle Q. Okay. This is a standing wave, so the amplitude of point P is like this, and the amplitude of point Q is like this, so it's less. Something like this. It's okay, I suppose. Calculate the speed of waves on the string. Calculate the speed of waves on the string. Okay, this is a standing wave, and for this case, if it's closed at both ends, we can say that the length equals 1.5 times lambda. Lambda, the wavelength, equals 2/3L, which is 1.6/3 meters, time the period. The period is, you can see that it's 2.8 seconds from the graph. 2.8 seconds. So the speed of a wave, of this wave, equals the wavelength of this wave divided by the period of the oscillations of this wave, which is 1.6/3 times 2.8, and we will get 190 meters per second. It's suggested that the speed c of waves in the string is related to the tension force T in the string, according to the equation T equals AC squared, where A is a constant. Determine the fundamental SI unit for A. From here, A equals T/C squared. In units, in terms of units, it's newtons. Newtons times seconds squared divided by meters squared. But we know that newtons, it's kilograms times meters per second squared, right? So we will get here kilograms times meters times second squared, right? Kilograms times meters times second squared divided by second squared times meters squared. We will lose seconds squared, square here, meters. So we will get just kilograms per meters. Okay, this is just the linear mass density, right, of the string. So this is the fundamental SI unit for A, kilograms per meters. The tension force of the string is doubled. Describe the effect, if any, of this change on the frequency of the standing wave. The tension is doubled, so we can say that T2 equals 2T1, right? And From the equation, we can see that c, the speed of the wave, equals the square root of t over this constant a. Now we know what this constant about. This is the linear mass density, but it just says that if we increase the tension by a factor of 2, the speed will be increased by a factor of square root of 2. Because the wavelength is still the same. We deal with the same standing wave here, and it has fixed wavelengths here. So that's all. It's increased by a factor of square root of 2, and if the speed is increased by a factor of square root of 2, we know that actually frequency equals c over wavelength over lambda. So if c is increased, f is increased by the same way, by the square root of 2. This is the answer. The standing wave on the string creates a traveling sound wave in the surrounding air. Outline two differences between a standing wave and a traveling wave. Two differences between a standing wave and a traveling wave. Traveling waves transfer energy and standing waves don't. Amplitude of oscillations varies along a standing wave and constant along a traveling wave. I think it's enough to say here. A mass is attached to one end of a rod and made to rotate with constant speed in a vertical circle. The standing wave on the string creates a traveling sound wave in the surrounding air. Outline two differences between a standing wave and a traveling wave. Standing waves have nodes and antinodes, traveling waves don't. Points in an internodal region have same phase in standing waves and different phase in traveling waves. Also, I can say that traveling waves transfer energy and standing waves don't, and amplitude of oscillations varies along a standing wave and constant along a traveling wave. Number 4. A mass is attached to one end of a rod and made to rotate with constant speed in a vertical circle. The scale diagram shows the weight of the mass at an instant when the rod is horizontal. Draw on the scale diagram an arrow to represent the force exerted on the mass by the rod. I think it's obvious that this force will be directed somehow like this. So it has to have the same vertical component as the weight, two squares, and we are not sure about the horizontal length, so we can make it as we want. For example, we can make it like this, right? We also can write down here that we are not sure about the horizontal length of this vector, but we are pretty sure about the vertical length of this vector f net. So it's f net vertical equals weight, right? Explain why the magnitude of the force exerted on the mass by the rod is not constant. It's not constant because the acceleration of the mass is directed in different directions, right? It has different directions. Here it has direction like this, here it has direction like this, here like this, here like this. So again, if we compare tension and weight, we know that at this point tension and weight, they have the same direction, and at this point tension and weight, they have opposite directions. So for sure For sure, the net force exerted on the mass by the rod is not constant, because the tension, the force of tension of the rod and the force of gravity, weight, they have different directions at different points. Number 5. Resistor R is connected in a circuit with a cell that has internal resistance. The ammeter and the voltmeter are ideal. State what is meant by an ideal voltmeter. It means that this voltmeter has resistance that goes to infinity. So it's much more greater than all the resistances in the circuit. Very high resistance. So no current goes here. The cell has an EMF of 1.49 volts. The resistance of R is 50 ohm. The voltmeter reads 1.47 volts. Show that the internal resistance of the cell is about 0.7 ohm. We can show it easily, right? We just say that the cell has an EMF. Okay, EMF equals 1.49 volts. R equals 50 ohm. The voltage that the voltmeter shows equals 1.47 volts. And the internal resistance, this is what we want to find here. And we can say that the EMF of the cell equals the current through the cell times capital R plus small r internal resistance plus external resistance, and I can say that it's I capital R plus I small r, and I capital R, this is what the voltmeter shows us. So the small r, the internal resistance, equals epsilon minus the voltage that the voltmeter shows us divided by current. But also I can say that current equals V over R, right? Current equals V over R. V, this is the voltage drop on this resistor, the external resistance capital R, and this is the voltage drop on this. And according to Ohm's law, we can derive the current like this. So we will substitute it here, and we will get EMF minus the voltage drop on the external resistance, the resistor R, times R divided by V, this voltage. And we will get something about 0.7 ohm. This is the internal resistance of the battery of the cell. Determine the total power dissipated in the circuit. The total power dissipated in the circuit equals I squared times external resistance plus internal resistance. So we will get V over R squared times R capital plus small r, which equals approximately 0.043438 watt. Yeah, or we can say that it's 43.8 milliwatts, right? And that's all. C. One of the connecting wires is placed in a magnetic field. The direction of the current in the wire is shown. Explain by reference to charge carriers in the wire how the magnetic force on the wire arises. If we have a moving charged particle in a magnetic field, this particle will experience a force from this field, from this magnetic field. You can call it a magnetic force. The force that it experiences equals the charge of its particle times the speed of this particle times the magnetic flux density B. It's just the strength of the magnetic field, and times sine of theta, where theta, this is the angle between V and B vectors, but in our case we don't need to talk much about this sine of theta. We just have to say that, yeah, it depends on the charge, on the speed, on the magnetic field itself, and yeah, we also call it a Lorentz force. So if we have a charged particle moving in the magnetic field, it will experience a force from this magnetic field, always. We also can find the direction of this force, and the direction of this force is into the page. Okay. Every current carrying wire produces a magnetic field. Describe one piece of evidence that supports this statement. For example, a magnetic needle is deflected by nearby currents. We know it's called Oersted's experiment, right? Or we know that two parallel current carrying wires exert a force on each other. Two wires with a current in the same direction will attract each other. Two wires with a current that has opposite directions will repel each other. And the last one, number 6, outline by reference to nuclear binding energy why the mass of a nucleus is less than the sum of the masses of its constituent nucleons. We know again that delta E equals delta m c squared. Energy is released when nucleons come together. So if we want to separate them, we have to spend some energy on it. And this energy that is released when nucleons come together, this is that mass defect. We call it a mass defect. That's why mass of a nucleus is always less than the sum of the masses of its constituent nucleons, of neutrons and protons. Okay, polonium-210 decays by alpha emission into lead-206. The following data are available: nuclear mass of polonium, nuclear mass of lead, mass of the alpha particle. Calculate in mega electron volts the energy released in this decay. Okay, so polonium decays, polonium-210 decays into lead-206, and we have an alpha particle. Initial mass equals 209.9367 U, atomic unit of mass. M final mass equals 205.92945 plus 4.00151, which equals to 209.930996 U. So delta M, mass defect, equals 0.0058 U. And we know if we want to convert this mass defect into energy, we don't have to remember this, but you have to know that you always can find this. One atomic unit of mass is equivalent to 931.5 mega electron volts, and we will use it to convert this defect of mass into energy. So let's just multiply it by this number, and we will get delta E equals, we will just multiply this, this number by this number, and we will get 0.0058 times 931.5, which is approximately 5.4 mega electron volts. The polonium nucleus was stationary before the decay. Oh, is it? Did I answer the question? Yeah, I answered. Okay. The polonium nucleus was stationary before the decay. Show by reference to the momentum of the particles that the kinetic energy of the alpha particle is much greater than the kinetic energy of the lead nucleus. Okay. The momentum of alpha particle plus momentum of lead particle has to be equal 0, because before the polonium nucleus was stationary, had 0 momentum. So it means that the momentum by magnitude, the momentum of alpha particle has to be equal to the momentum of lead. But kinetic energy equals momentum squared over double m. So it means that the ratio of the kinetic energies, kinetic energy of the alpha particle over kinetic energy of the lead, equals the ratio of their masses, because their momentums, they're equal to each other. So mass of lead over mass of alpha particle, which is about 206 over 4, which is approximately 51.5. Wow. So they said, show by reference to the momentum of the particles that the kinetic energy of the alpha particle is much greater. Yes, it's much greater, about 50 times greater. In the decay of polonium-210, alpha emission can be followed by the emission of a gamma photon. State and explain whether the alpha particle or gamma photon will cause greater ionization in the surrounding material. An alpha particle is massive and has charge plus 2 elementary charges. So it interacts pretty strongly with electrons in atoms via Coulomb's forces. Loses its energy over a short distance, right? And a gamma photon is uncharged and interacts only indirectly with matter, like photoelectric effect, Compton scattering. So it's much less ionizing per unit path length, but it's more penetrating. So gamma photon is more penetrating than alpha particle, but alpha particles can cause greater ionization. Alpha particles can cause greater ionization, but gamma photons, they are more penetrating. And it's enough to say here